Well, hello. Welcome to the Future Internet course. And we are going to start this class on data plane programmability with the introduction and some applications. This class will be divided in two videos. This first video will have like a motivation for data plane programmability. In the last classes, we were talking about SDN, the difference between the control plane and the data plane. We talked a little bit about OpenFlow, but we are going to see why nowadays it is thought that OpenFlow is not enough, and we need also some programmability in the data plane, not just in the control plane. So in the agenda, we're going to see OpenFlow and SDN, the innovation in traditional switches, some domain-specific processors, the top-down normal network programming paradigm, programmable switches, P4, which is a programming language for the switches, and then some applications. The material of this talk is taken from the talk of Nick McCune in SIGCOMM 2017. You can go to the YouTube link there if you want to see his entire presentation, which is actually very good, and also a presentation from Luciano Gaspari, a professor from Brazil, called Security and SDN and Data Plane Programmability. You also have access to the video in this link. So let's start with OpenFlow and SDN. So OpenFlow is a common, as you know, open vendor agnostic interface that enables configuring forwarding devices from the control plane, right? So you can program the control plane to indicate the, let's say the switch or the networking device what to do. It is the de facto standard for enabling the SDN main concept of control and data planes separation. And it decouples the project and development of the different planes, right? So as we saw now, the control and data planes are decoupled thanks to OpenFlow. And now control and data planes can now evolve independently, right? As you know, and we have already seen, this is the architecture of OpenFlow. So we have the applications on the top of the figure. So you can see here in a monitoring application or a routing application, or I don't know, any application. Then you have the network operating system or controller that we saw, which can be Knox or POX or Open Daylight or all the ones we saw. Then you can install or query with forwarding rules through the OpenFlow protocols to the OpenFlow switches, right? And then here in the flow tables of the switches, you install the rules as we just saw in the last lessons. Which are the advantages of OpenFlow? We know that it has enabled great innovation in the control plane. The control plane application now leverage global view to take more informed configuration decisions with the global view of the network. However, besides the decoupling, OpenFlow has not brought much change to the data plane innovation. And we saw a lot of innovation in the control plane as we can program the control plane, but we didn't see anything in the data plane. Innovation in the data plane is still limited. Network operators are always looking for new forms of packet, but we have the standard form of packets that is limited by the data plane protocols, right? So what happens when a network operator needs a new protocol to be implemented in the network? Let's see how is the innovation in traditional network. Let's see this cartoon picture to motivate why this is important to program the forwarding planes for building new networking systems. So this is a figure of the insides of an enterprise switch or router, right? It runs a switch OS, and that today is normally always based on Linux or BSD Unix systems. The switch OS talks to the switch ASIC using a driver, right? So you go to the ASIC, the chip of the switch using a driver, and for every protocol and feature, There is a user level process that exchanges routing table information with the neighboring switches, right? But let's see, let's think that now we have some customers in our network, for instance, a data center that are asking for a VXLAN tag in the packets. VXLAN is or was a new way to tag packets in virtualized data centers to identify the tenant the packets belong to. So the equipment vendor needs to write the VXLAN software to control the switch, right? So you have to write this to control the switch, and they need to update the driver, right? To be able to add and delete entries in the switch ASIC, right? So the driver, and then you have to modify the ASIC too. To modify the software is a few weeks or at most few months work, right? But you have to update, the switch ASIC because VXLAN requires processing packets in new ways because you have a new, let's say, field in the packet, and this field has to be processed by the switch. So you have to change the ASIC of the switch. And the development of new ASIC features in the switch, for instance, in the case of VXLAN at the beginning of the 2010, took actually 4 years. So it took 4 years to show up in the switch chips used to build switches and routers. And this was actually in the most profitable, most invested part in networking because this was for data centers. So what happens? What happens is the following. Then you have the network owner that is asking for a feature to the network equipment vendor, right? Cisco, Juniper, any of these guys. These guys identify a problem, right? And the network equipment vendors then go to the ETF to figure out a solution and publish a new RFC. Then define the feature in the software team with the feature writes the software, maybe in weeks or months, right? But when it comes to the ASIC team in the switch, then you ask to go to the actually chips in the switch, ask for one feature, and this can take years, right? So 2, 3, or even 4 years to implement a new feature in the ASIC of the switches. So this is a process that just to say, okay, in my packets, I need a new tag, and I need that when this tag is put in the packet, the switch should do this or this other thing to implement that in the switch interface, and then for the switch vendors to be convinced and then to invest in this implementation, and then for the let's say for the network owners to again buy new hardware because this new hardware is with the new feature. This takes a long time, and also is it costs a lot of money, right? So when you need a new feature, equipment vendor can't just send you a software upgrade. You can't do that because the chip of the switch, the ASIC, will not support that new feature. So new forwarding features take years to develop. By then, you have already figured a clutch to work around it, and with this clutch or this patch, your network gets more and more complicated, more brittle. So eventually, when the upgrade is available, it either no longer solves your problem, or you need a forklift upgrade at huge expense because you have to, again, buy new network equipment, right? So the thing is that network systems are built bottom up. So I am the switch, which is a fixed function switch nowadays, right? And I tell the switch OS and the driver, hey, guys, this is how I process packets. I just know how to process IPv4 headers or IPv6 headers or MPLS headers and TCP headers, UDP headers, and so on. I mean, if you have a new header in the packet, I don't know what to do. I cannot process a new feature. Okay, and taking that into account, so the switch OS will be able just to write instructions for these headers or for this way of packet processing of the fixed function switch. So this is why it's bottom up. We can just do whatever the chip tell us it is able to do, right? So why not rethinking a little bit? We need to rethink how we design and configure our networks. So think on something, right? When the computing started, right? Uh, we had also the same, right? Now we have CPUs that with Java and some compiler or any other programming language, you can tell the CPU maybe how to work, right? For computers. For graphics, you also have specific chips like GPUs where you can configure exactly in a good way the application for graphics. For signal processing forever, you have DSPs to process the signal processing information. Also, you have for machine learning nowadays, they are starting to work with this, for instance, with this TensorFlow programming language with a compiler that will be processed by a TPU. So especially designed for this kind of machine learning applications. But what happens with networking? We don't have that. I mean, we use normal CPUs for the normal chips, sorry, fixed function chips in the switches. So there is not a possibility, there isn't a possibility to actually define new headers or new ways to process packets in the switches if I cannot program the chip, right? So unfortunately, what we had at the right at the left-hand side just hasn't happened in networking because no one stepped back and asked how to build the right domain-specific processor for processing packets or networking packets. And this is something that changed a little bit in the last few years, 3 or 4 years, with something called the PIS architecture and the P4 networking language or networking programming language. Okay, uh, what we have now with this initiative is domain-specific processors, so networking-specific processors. So why isn't there a programmable chip optimized for generic packet processing that is able to generically parse fields, look up tables, and processing actions? So, okay, now there is some kind of these chips. Then the idea that the networks could then be programmed top-down and not bottom-up. So I tell actually from the switch OS, from the operating system with the driver, I tell the programmable chip, the programmable ASIC, the programmable switch, what I want it to do. So I can tell the programmable switch, this is precisely how you must process packets. I am creating a new tag. I need this tag for this thing, and I need you to process this tag in this way. And I can indicate how to process it using a programming language that is called P4. Here, there is just some code of P4 that we are going to see in the next lesson, actually. So this is very revolutionary, I think, for networks, right? Because I am telling the network how to process the packet. And there are now so programmable switches, some programmable chips. One is the Barefoot Tofino that can reach the speeds of up to actually 12, almost 13 terabits per second. Is the world's fastest switch in production and it's programmable. The forwarding behavior is defined in software, and programs always run at line rate. So this is a very nice chip that you can. So you can now buy a Barefoot switch, which is totally programmable, right? So how do you program this kind of switches? So you program this kind of switches with a programming language called P4, or programming is called Programming Protocol Independent Packet Processors. But we're going to see more details of P4 in the next video. Okay, thank you very much for your attention. And in the next video, we'll start with P4. Thanks a lot.